Here are the sample problems for class 20 of Math 117. I apologize for the voice quality. It's not the fault of the microphone. I've had a bad cold and am just barely starting to recover. So in the first problem, we're going to build a two-stage scratch ticket using the same sort of strategy that eventually will lead to the Black-Scholes equation. And the way we're going to do this is by saying at one stage of this ticket, the price either gets multiplied or divided by a factor v, which in this case is going to be 3/2. And then, in order to make the process a martingale, it's going to be multiplied by a factor m, which I'm going to take to be 6/5. So that's enough information to figure out the up and down factors. Let's first work out the factor by which the share price gets multiplied. That's equal to m times v, which is 3/2 times 6/5, or 1.8. If the share does not do well, it gets multiplied by d, which is the inverse of v, 2/3 times 6/5, which is equal to 12/15, or 0.8. Well, you can see that the shares are either going to go up a lot or down a little bit. That must mean there's a small probability for the shares to go up, and you already know the formula for that. The probability of going up is 1 minus d over u minus d. That's 1 minus 0.8 divided by 1 minus 8, 1.8 minus 0.8, or 0.2. So now we can figure out what's going to happen at each step. We'll start out at initial price of 50 with a probability of 0.2. That will get multiplied by 1.8 and will go up to 90. With a probability of 0.8, it will go down to 40. And the same thing happens at the next, and indeed any number of subsequent steps. So at the next stage, with probability 0.2, the price skyrockets to 162. With a larger probability of 0.8, it drops down to 72. And from 40, it can either rise to 72 or plunge further to 32. So this is a much more consistent sort of scratch ticket that we were using earlier, because the same thing happens at every node at every stage. Now, there's another set of variables we can keep track of. The variable a sub I is just +1 if the share price goes up, -1 if it goes down. And w sub n is the sum of the a sub i's. So let's write in the values of w sub n in circles. There's 1 and -1. There's 2, 0, and -2. Just a standard sort of random walk. Now, we know the probabilities for these final states: 0.04, 0.32, and 0.64. And if I look at the expectation of the share price on day 2, that's X2, I get 0.04 times 162 plus 0.32 times 72 plus 0.64 times 32, and trust me, that works out to our initial 50. We've got a perfectly good martingale here. Unfortunately, W sub n is not a martingale. If you look, for example, at the expectation of W1, it's 0.2 times the value of 1 plus 0.8 times the value of minus 1, which is minus 0.6. That's not equal to W0, which was 0. And if I go one stage further, I get 0.04 for the value of 2 plus 0.32 for the value of 0 plus 0.64 times the value of minus 2, and that's equal to minus 1.2. And you can see what's going on. This is just dropping by 0.6 times each time. So if I choose C equals 0.6, that makes what Deneen calls W sub t tilde. That's W sub t plus CT into a martingale. Now we'll try something a little bit different. In the previous problem, I allowed the probability for going up and going down to be different from a half. This time I'm going to constrain that to be a half and instead make the share price be a martingale by picking the right value of M. So, what do we need? For a martingale, a necessary condition is that 1/2 times the higher price plus 1/2 times the lower price, which is 1/2 times SMV plus SMV inverse, had better be equal to S, or since S as always drops out, M times V plus V inverse is equal to 2, and M is equal to 2 over V plus V inverse. But now I'm going to write this in terms of an exponential. I'm going to denote V by e to the sigma. So I have 2 over e to the sigma plus e to the minus sigma. And now I want to get a nice approximation out of this by using Taylor series. So I'll say e to the sigma is 1 plus sigma squared over 2 factorial plus more terms. E to the minus sigma is equal to 1 minus sigma plus sigma squared over 2 factorial plus other terms. And therefore the sum, e to the sigma plus e to the minus sigma, is equal to 2 plus sigma squared, and m is approximately. It's only approximate because we threw out higher terms involving powers of sigma higher than 2. I get 2 over 2 plus sigma squared, or 1 over 1 plus sigma squared over 2. But if I write that as 1 minus sigma squared over 2, I'm just throwing away a term involving sigma to the 4th. We've been doing that earlier, so that this is consistent. And now what happens if I choose mu equal to minus sigma squared over 2? Then m, which is e to the mu by definition, is e to the minus sigma squared over 2, which is, using a Taylor series approximation again, approximately 1 minus sigma squared over 2, which proves the result I had in mind, and which concludes the shortest set of sample problems so far.